Hello, this is section 5.3 exponential function and models. And okay, so let's start from the here. So we talk about the linear, and then now we're going to talk about the exponential growth. So linear function as a fixed number to the previous value of y for each unit increases in x. So example was f of x equal to 10,000 plus 500x, which is because of the x that is a linear. And also the exponential function is going to be the multiplies a fixed number by the previous values of y for each unit increase x. So which is we multiply the same number. So which is your x you gotta see over here. So it's exponential function base a and then coefficient c. So this is a graph of the exponential function because you multiply the numbers and then you adding the number to get the linear functions. So in order to see the x is increasing by 1, but for the y value is actually the multiple by 2. And then for the linear function, x is increasing by 1, and then it's adding by 2 this time. Okay, so that's the difference. So linear function is adding constant, and then the exponential function is multiplying constant. All right, exponential graph has two way of the graph. So first one is the increasing graph, which is we call the growth, and then the decay graph, which is but it depends always about the coefficient though. So when you have a coefficient is the base a is greater than 1, it's always growth functions. It's increasing, and then it's between the 0 to 1 is always decreasing. So graph of y equal to a to the x power increasing when a is greater than 1. So when a is greater than 1, the graph exhibits exponential growth. So yeah, see, as long as base is greater than 1, yeah, it's all increasing. And then y equal to ax is a increase. Oh, should be decreasing. Okay, so that's a typo here. Should be decreasing when a is between the 0 to 1. So graph is exhibit exponential decay. So it's getting smaller, right? Yeah, exponentially. All right. So let's look at the number one. For each table, find either is a linear exponential function that the model the data. So as you notice, x is increasing by 1. And then I want to check with the decreasing. So decreasing by 3 and decreasing by 3. So consistently, you keep adding the negative numbers. So I can figure out the next coordinates, which is a 3, and then subtract 3 from the 4 should be 1. So this is a linear because it's decreasing by 3. So subtracting by 3, okay? And B, adding by 1 as x value, but it is increasing, so plus 4, but this is a plus 12. Okay, so this is not a linear. Because of this, it's not a linear. Now, I can think about it as a multiplier. So 2 goes 6 by 3 times, and 6 goes 18 by 3 times. Okay, all right. Because of multiple by constant number, we can call this as an exponential. Okay. All right, so property of the exponential function. So we have to have general forms of c times a to the x power. So a is a positive. Oh, a is always positive. Okay, a shouldn't be a 1 because a is a 1. You get the the constant function. So for the exponential functions, the domain is always a real number, but range is always above the 0 for this case, which is if your function is f of x equal to c a to the x power plus, let's say, d, and then the range is here, you can say from the d to infinity, okay? All right, if that's uh, the coefficients are actually the positive number. And then graph of f is continuous with no breaks, and there's no jump, there's no break, okay? X is horizontal, x intercepts. There's no x-intercept for this time. The y-intercept is always 0, see? If the a is greater than 1, f is an increasing function on the domain, and a is between the 0 to 1 is a decreasing all through the domain. And then function is 1 to 1, and therefore it has an inverse too. So example 2, so find the value of the c and then the a through the given conditions. So I'm going to start one at a time. So I'm going to use f of 0 equal to 6, okay? So f of 0, which means you plug it in x as a 0. But f of 0 same as a 6. Oh, this is a 0, sorry. You have to plug it in 0 for x, which is a to the 0 power is actually the 1. So which is c equal to. Now I'm plugging in. The x is a c is a 6 times a to the x. Now I need to find the x value. Now I want to use the second condition, which is f of 1 equal to 3. So f of 1, 6 times a to the first power, which is equal to 3, and then divide by 6, a is equal to 1/2. Okay, so now we have this function should be 6 times a is a half to the x power. So make sure that you put the pencil around the base though. Otherwise, you might simplify. Okay, so and the next problem. Okay, there's f of -1 is 1/9. Okay, so what I do is I try to figure out CNA for the exponential general form. So I want to do the one at a time. Okay, so f of -1, which is CA to the -1, same as 1/9. So what I got is it's gonna be C over A. Okay. So what I have here, so I said A is a 9C. Okay, so I want to keep it still. We don't know what is A and C yet. For the second one, f of 1 equal to 1. So f of 1, CA to the first power, which is equal to 1, and then CA. Okay, now I can substitute for A as a 9C. So 1 equal to C, A is the same as a 9C, which is 1 equal to 9c squared, and divide by 9 both sides. 1/9 equal to c squared. And then square root on both sides with a plus minus. C is a possible for plus minus 1/3. Okay, and then so she could be positive or negative this time. Okay, so and then but you have to think about the graph of the behavior here. X is -1 is 1/9, 1 is 1. Oh, so it's increasing. So I have to take it as a c the positive. So I only take the c as a 1/3. So once you have a 1/3, you need to plug it in. So if you plug it in right here, right now. Or you can plug it in here too. You can plug it in here if you want. Okay, so a is equal to actually the 9 times 1/3, which is a 3. So a is a 3, c is a 1/3, so your function is 1/3 times 3 to the x power. Alright, number 3. A sample of a bacteria doubles in concentration in each day. Initial concentration is 1.5 million bacteria per milliliters. So A, find a function that gives the concentration of the bacteria after t days. Okay, so I want to say general form c times a to the x power because it says they're talking about double, which is a multiple by 2, right? So in here, so initial value, so c is actually the initial value. Okay, so initial value was 1.5. C is a 1.5. And also, it makes a double. So your base is a 2. Makes a double means a 2 times. Okay? So that's all for this function. And then we want to estimate the concentration for the 4.5 days because x is actually the number of the days. So f of 4.5, which is 1.5 times 2 to the 4.5. Use a calculator. It gives you another 33.9. But the unit is going to be the million. It's going to be millions. So that's the number of the bacteria. All right, number 4. Explain how to obtain the graph of g from the graph of f of x equal to 2 to the x power. Then graph both f and g on the same x and y plane. All right, so I'm going to graph this one by using a table, which is, I'm going to use a -2, -1, 0, 1, 2. And then plug in -2 become 1/4, 1/2, 1, and 2, and 4, okay? So -2 is 1/4. -1 is 1/2, 0, 1, 1 and 2, 2 to 4, okay? So you got this graph. So this is a graph of f of x, okay? Now, as you notice from the g of x, it says a -1 from the x, right? So which means you need to go left to the 1 unit. So all the points just go to left to 1 unit. So 1 unit left right here, 1 unit left, 1 unit left, and 1 unit left, 1 unit left, okay? And then if you connect them, and then there'll be the graph of g, okay? So using a transformation, or you can use a table too. And this time, difference from the f and g is negative, okay? So if you draw the graph of the 2 to the x power, you got -2 1/4, 1/2, 0, 1, 2, and 2 to 4. This time, we're going to flip it, okay? This is actually the reflection about x-axis, okay? Because the vertical reflections. So instead of the 1/4, I got -1/4, flip down, okay? -1/2, -1, -2, and -4, okay? So you got the graph is upside down. So this is a graph. All right, because of the exponential functions, we can use the compound interest formulas. So if a principal P dollars in deposited on the account paying an annual rate of the interest R, expressed in decimal, compounded, paid, and times per year, then after T years, the account will be contain $8, where this is a form, okay? So which is A is the balance after T years, and then P is a principal, which is how much that you invested, and then the R is interest rate, annual interest rate, providing the decimal, and the N is actually the interest period. Okay, so N equal to 1 means annually. N equal to 2 means semi-annually. N equal to 4 means quarterly. N equal to 12 means monthly. And just think about that, how many units in a year, okay? And then N equal to 52 means weekly. N equal to 365 for the daily. Okay, and then you can go further if you want. All right. So in number 5, find if the principal is 1,500 and the interest rate is a 7% compound annually, calculate the amount after the balance after 10 years. So first of all, principal is 1,500 deposited, and the rate is annually 0.07, and the annually, which is just the once a year for 7 years and 10 years, and then T equal to the 10, okay? So balance for the amount is P times 1 plus R over N to the N-th power. So P is 1,500, 1 plus interest rate is 0.07 for the annually, and then 1 times and the T is 10, which is about $2,950.73. And then number 6, suppose the 2,000 is deposited by the worker in an individual retirement account IRA that pays an annual interest rate of 6%. Describe the effects on the balance after 30 years if the interest were compounded quarterly rather than the annually. Okay, so P equal to now $2,000 interest rate is now the 6%. And then n equal to quarterly, which is a 4, and for 30 years. Okay. So a equal to p was 1 plus out of n and t. And then you get 2000, 1 plus 0.06 over 4 to the 4 times t, which is 30. And then you get the $11,938.65. Yeah, pretty good, right? But what if you use the same, everything's the same except the interest period, which is 1, because annually it's t equal to 30. So in order to find it, p is 2000, and 1 plus 0.06 over 1 times 30, and then it gives you the $11,486.98. And then if you see the difference between the quarterly to the annually, and then it becomes $451.67. So this is how much you earn if you use the quarterly instead of the annually. Okay, example 7. So let f of x equal to 2 times e to the negative 0.05x. So we're going to figure it out. So just plug it in. So first x is 1.2. Now you got to use the calculator, okay? So negative 0.05 and times by 1.2 as a power. Then approximately I got 1.884. And then you can plug it in negative 4 because x is all real number as a domain. 2 times e to the negative 0.05 to the negative 4, you got 2.443. So it's not bad if you use a calculator. Now, we also have a continuous compounding, the interest formulas, which is this time is this is actually becomes the this is actually the when x is goes to infinity, and this is actually goes to the close to the e. So that's what we use the Euler number. So this value is so important. The mathematics that has been given is on symbol e, sometimes called the Euler number. The number e has many of the same characteristic as a pi. Its decimal expansion never terminates or repeated in pattern, so it is still the irrational number. So value of the e is approximately this much, but your calculator already had that, so you don't have to, actually find it. So we have to use a natural exponential function. So basis now becomes an e. So if you do the continuously the compounding interest formulas. So okay, let's look it up. So continuously compounded interest. So if a principal P is deposited in an account paying an annual rate of interest of R, expressed in decimals, of course, and compounded continuously, then after 2 years, the account will contain $8 where, and this is a formula for the continuously compound interest. So let's think about number 8. So the principal in RA for 2000 and the interest was 6%, but we're going to put that as a compound continuously for the 30 years. So we don't need the interest period because it becomes continuously you're earning the interest, okay? So this is going to be A equal to PERT, so 2000 e to the 6% for 30 years. And then you got $12,099.29, so which is more than the quarterly. So natural exponential growth and decay. So this is what we can use the function that to find out the growth or decay for the problem. Okay, so yeah, this is a formula that we use here. Okay, so how do you know it's a growth? Because k is a positive. How do you know it's a decay? It's a k is a negative. So growth means this is a graph of growth. It's getting increasing, and getting decreasing we call the decay. So on number 9, let's think about this. Okay, so sometimes after the patient take a drug, the amount of the medication A in the bloodstream can be modeled A equal to A sub 0, e to the negative RT, where A sub 0 is the initial concentration in the milligram per liter, R is the hourly percentage decreases in decimal form of the drug in the bloodstream. And then T is the elapsed time in hours. Suppose that the drug concentration initially 2 milligram per liter, that is R equal to 0.2. So find the drug concentration after the 3.5 hours. So the T is hours. So what I do is A sub T equal to A sub 0 e to the negative RT. So for 3.5 hours, so initially it was 2 milligram e to the negative, and then the percentage of in here R is already 0.2 as a given, and then times for 3.5. So when you compute that, you got the 0.99. So that's how much in the bloodstream. When did the drug concentration reach to the 1.5 milligram per liter? So if you use a calculator, so for the function of the amount of the medication in the blood, I want to use a t to the e to the negative 0.2 t to graph this, okay? And then for the 1.5, so this is about here. So you can use a calculator, okay? That's easy. So about that time was, it will take about 1.44, about this number, okay? 4 hours. And then number 10, the table lists the concentration in the sample of the E. coli bacteria B in billion per liter after T hours. So find the value for C and CA to the X and model of this data. So yeah, so I'm using this two order pair, okay? Or you can use either one, but I like to use X equal to 0. So f of 0, which is 0.5, right? And then f of x, which is a c times a to the x, which is f of 0, is going to be ca to the 0. F of 0 is 0.5, which is c. C is a 0.5. Now, your f of x is a c is a 0.5, but we don't know the x yet, okay? A yet, base a. Now, I'm using the 5 as x, so 0.5 times a to the 5th power. And then f of 5 is 33.3 over equals 0.5 a to the 5th power. And then if you divide by 0.5 both sides, you get the 66.6, which equal to a to the 5th. So in order to get an a by itself, you need to put the 5th root on both sides, 66.6. And then about, you got 2.316. So now your function should be the 0.5 as a c, 2.316 as a base, which is a, and to the x power. And then now you can find the x is hours, so after 6.2 hours, 0.5 times of 2.316 to the 6.2, which come out as 9.3, which means that the bacteria concentration after 6.2 hours is about 91.3 billion per liter. So it increases. All right, the next page. Okay, so economists study for the spacing between the individual trees in the forest in the British Columbia. The probability or likelihood that there is at least one tree located in a circle with a radius of x feet can be estimated by these formulas, okay? For example, after t come out as this, if you plug it in 7 in here, you get these values. Means that if the person picked the point of the random in the forest, there is a 55% chance that at least one tree will be located within 7 feet. So you need to figure out P of 2 and P of 20. So P of 2 is, so which is like a 2 feet distance, right? So 1 minus e to the negative 0.1144 times by 2, and then I got about 0.20. And then 20, which is 1 minus e to the negative 0.1144 times by 20, I got 0.90. So interpretation means this means that there is a 20% chance that at least one tree will be located within the circle having a radius of the 2 feet. And also there's a 90% chance of at least one tree being located within a circle with a radius of the 20 feet. And the B, graph so actually I graph for you too. So this, if you graph these functions using the graphing calculator or the Desmos put showing it, yeah, this is what it is. Okay. And then does the have a graph as a horizontal asymptotes? Yes, it's kind of not actually the greater than 1 this time. Okay, so which is 1 right here. So it stays actually getting closer, but it stays a 1. All right, and then which is still increasing, right? But and then for the third is now we are looking for the distance that 50%. Okay, which means p of x is 0.5, which is you got the find out the 0.5, which is half of it. So about how much that is. Okay, so which is half of it about here. So you just need to find out what number that is. Okay, so if you use a graphing calculator and p of x equal to 0.5, and then x is about to be 6.1, which is you get like a 6 feet, 6.4 feet away, then you can have the 50% chance to contain at least one shoe. All right, next problem, modeling half-life. So half-life, in order to find the half-life, we're using the A's of 1/2, okay? Okay, so that's what we call the half-life. So the initially link of the Facebook had no hint, and 100% of its hits are not to occur. Write an exponential function f that give you the percentage of the engagements yet to occur on typical Facebook link if the half-life is 8 hours. Estimate this percentage after 4 hours. So first of all, I want to say f of t equals to t times 850. So for the 0, it says 100%, and then 8 and 3 can half of it, so 50. It takes actually the half-life is 8 hours. Okay, so this is it. So when you have a full percentage on the 0 hour and then about 8 hours, you got the 50 percent, whatever it was. Okay, so f of 0 equal to c to the a to the 0, which is f of 0 was 100. So c is actually the a sub 0 is a 1, right? So c is 100. Okay. Now plug it into the as a t, which is c is 100 now, a to the x. Now I'm using the t as 8, and then 100 a to the 8th power. So f of 8 is about 50 because half. And then a to the 8 is going to be 1 over 2. And then a is by sub is 8th root of 1 over 2. And then the 8 becomes to the I can just leave it as a 1/2 to the 1/8 power. So now your function is f of t is c is 100 times half to the 1/8, and then you put on the t. Okay. All right. Now we need to find the f of 4. Now what about 4 hours? So half of 1/8 times of 4, and approximately goes to give you the 70.7, which is the percent left. Examples 13. A fossil contains 35% of the amount of the carbon-14 that the organism contained when it was alive. Graphically estimate its age though, but you can just find it here. So a of x equal to, so c times, and this is actually we can use a half life formulas. Okay, so x over the k, or t over the k. Okay, so now this time when you have 100%, you left it as a 35%, right? And half of for the x over, and then the k is, when you're using those to figure it out, is 5,700. So in order to solve for x, you get the 8633. Okay, so that's the age it takes to get the 35%, the amount of the carbon is left. All right, okay, so thank you for listening.